Hi there, students. It's Mr. Pouts here with what lesson are we? Section 5-4. Now, originally, you can see on the front here, it just says Happy Day. It said Happy Wednesday because originally this was made on a Wednesday, but you might not be watching it on a Wednesday, so Happy Day. Um, as we're going, the goal for today, for Section 5-4, we're continuing with this theme of interesting different relationships in triangles. And the relationships we're dealing with today are dealing with medians and altitudes. So please have the goal written down. It says I can identify and use properties of medians and altitudes of triangles. All right, and as you're doing that, you can see there's a nice picture in the back. That's actually from the 90s, I believe. It's a boy band from the 90s. If you can figure out who they are, what the band is, you should let me know next time we come to class. But we're going to go on. We're going to go right here. Some key vocabulary words. There's a lot of interesting terms that we have going on in this chapter, including what we've already done. We've done incenter and we've done circumcenter. We're going to add two more today that are like that are points where lines are concurrent inside of a triangle. But so the first one is a median. Well, the first one it has to do with, but a median of a triangle, not the median of a set of numbers. The median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. So if you draw it right here, you have the vertex and the midpoint. Let's say this is cut in half right here. So this side is congruent to this side. That segment that goes across from the vertex to that line, that's called a median. All right, and it's a little bit different than what we like an angle bisector. It's not going to necessarily bisect it. It's not going to be necessarily a perpendicular bisector. It could, depending on the triangle, but it goes from the the midpoint of one side to the vertex of another. So there's a picture. And a centroid, this is one of the ones that I was talking about. That's the point of concurrency of the medians of a triangle. So it's where they all cross. So if we have our one median, that's congruent. We have our second median, those are congruent. We have our third median, so those are congruent. That point where they intersect, they will all cross at the same point. That is called the centroid. Pretty cool word there, centroid. All right, next one, an altitude of a triangle. An altitude of a triangle. And I actually am surprised I don't have another term on here. But an altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. So it does not matter where it is, as long as it's from the vertex to, it's perpendicular from the vertex and perpendicular to the opposite side. So if we're taking this one right here, it has to be perpendicular, but it has to be also going through the vertex of that opposite angle there. So right there, that line is called an altitude. Basically, if it's sitting like this, it's the height of a triangle. Now it's hard to picture for this one, but if it's a right triangle, which this one almost looks like it's a right triangle, not quite, but it'd be going like this, from this vertex to here if this is a right angle. That would be another median. And the third median would be this one. It's very close to a right angle. So it's going to be something like that. So they do intersect at the same point. And I don't have that on here, but I'm going to add that to this. And these are in your notes at some point in time. But the orthocenter, can't believe I don't have that one on there. The orthocenter of a triangle is the point of concurrency of the altitudes of a triangle. So that's the last intersecting point, term for intersecting lines of a triangle. Where the altitudes intersect, that's called the orthocenter. We'll talk about how to find the orthocenter. So that would be right there, where they intersect. All right, those are the four main terms for today. Let's put them into context here a little bit and see what relationships they have. So let's start off here. Pretty essential thing to know for today is that triangles' three medians are always concurrent, and we said that's going to be at the centroid. So, but here's something to know: the length of the segment from the vertex to the centroid. So the length of the segment from the vertex to the centroid. The centroid is where all the medians intersect. Is twice the length of the segment from the centroid to the midpoint. So if we're looking at this line right here is twice as long as this line right here. We have it labeled right there. It'll be for every midpoint, or for every median, it's the same way. This one and this one. So let's say this is y, this would be 2y. Same thing with the third one. And there's actually a theorem that goes right with that, and it's in your notes. The concurrency of medians theorem. So another way to look at that is the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex. So if this is all one median, this would be 2/3 of that median. I know that's hard to see. But the longer part of it is 2/3. It's just broken up into chunks. If you think about it, one part is twice the other part. So then 2/3 of it, or 1/3 of it would be the smaller one. 2/3 of that whole median would be the larger part. And that's listed right here. DC would be 2/3 of DJ. EC would be 2/3 of EG. And FC would be 2/3 of FH. So let's use that. Got a couple examples here. We got to look at the example to the right. So in triangle VYX, the centroid is Z. So again, that's where the medians intersect. It's a hard thing to remember, but I think we're going to come up with some ways to remember that. The centroid is where the medians intersect. Then you have to know what the medians are. The medians go from the midpoint of one side to the vertex. So this Z is the centroid. If XR is 24, so XR, this whole line is 24, we know from the theorem that XZ is 2/3 of XR. Let's plug that in. It says find XZ and ZR. Well, if we know that that is that, so we'll say XR is 24. So 24 is 2/3 of XR. Multiply both sides by 3/2. Oh, sorry. Oh, no. I got this mixed up. 2/3 of 24 would be what XZ is. So XZ equals 2/3 of 24 would be 16. And that leaves ZR to be 8. Just whatever's left. And that makes sense. We said that the longer one is twice the smaller one when we're breaking up the medians. Same thing here. So VZ is 14. Find VP and ZP. Well, let's look at this. VZ is 2/3 of VP in this one. So let's plug it in. VZ is 14, and that's equal to 2/3 of VP. We multiply both sides by the reciprocal. Multiply this by 3/2, and this will cancel out. VP is going to be equal to whatever 2/3 of 14, or 3/2 of 14, that's going to be 21. And if 21, then the VZ is 14, then ZP, so if we label it, this would be 14. We know that right away ZP has to be half of that, so that'd be 7. That makes up a total of 21. That's where we get those two answers from. All right, let's look at the last one. ZO is 10. Maybe it helps the picture. I'm just going to label it 10. Well, then ZY has to be twice as that, or YZ. So I'm not using the theorem directly now. I'm just looking with what we said as our statement earlier that, slow here, that the length of the segment from the vertex to the centroid is twice the length of the segment from the centroid to the midpoint. So yz would have to be twice of 10, so then yz is equal to 20. And then we know the whole segment. I don't know why I said yz. Oh yeah, I did that. Then yo would have to be 20 plus 10, which would be 30. That's what all comes from this theorem, the centroid concurrency of medians theorem. In other words, it's kind of like the centroid theorem. All right, let's go on. I got another theorem for you. But remember, what is an altitude? Well, let's look back. An altitude is the perpendicular segment from a vertex of the triangle of the line to the line containing the opposite side. So it's basically the height of the triangle. So I'm going to squeeze that in here. I don't want to rewrite it. You already wrote it down somewhere. Hopefully, maybe you put it in the spot already. But it is, again, the perpendicular segment from a vertex of the triangle to the line containing the opposite side. It's very similar to the height. All right, Theorem 5.9 says concurrency of altitudes theorem. And remember, altitudes are concurrent at the point called the orthocenter. So it says the lines that contain the altitudes of a triangle are concurrent. Whew. It's a tough one to write down. The lines that contain the altitudes are concurrent. So we know that altitudes do all cross at the same point. The point of concurrency of the three altitudes, we said, is called the orthocenter. Like an orthodontist, only not. The orthocenter. All right, let's work with that theorem a little bit. Determine whether AB is a median, an altitude, or neither. So far we've been working with medians and altitudes and where they intersect. So if it's a median, altitude, or neither. So remember, medians go from the vertex to the midpoint of another segment of the opposite side, and the altitude is essentially the height. So it's perpendicular. It's a perpendicular line from the vertex down to the opposite side. So I'm going to look at these, and I'm going to say number 4. It looks like it could be close to either one, but for it to be a median, these two would have to be congruent. Since they're not, this is just an altitude. Next one, we have that they're congruent, so it's for sure, if it's going from there to the vertex, it's definitely a median. And it doesn't look like it's an altitude because it's not a perpendicular line to the opposite side. Now number 6 is it's definitely not a median because it's not cutting the CD in half, so this is going to be a perpendicular altitude. All right, so knowing the difference between those two. The other two examples here, I've got our name the centroid and name the orthocenter. So we're finding the centroid, we're finding the orthocenter. There's lots of lines going on in these things. They're not all medians or they're not all altitudes. You have to determine, number 7, what is the centroid. So remember, centroid is where the medians intersect. So if there's an altitude, we just ignore that. So the medians would be, let's see, I'll use green to show the medians. We'll say blue instead. The medians, again, so if this is congruent to this, then this line would be the median because it goes from the vertex, from that midpoint to the opposite vertex. Looks like this one as well. And that's all you need. All you need is 2 of the medians to tell where the centroid is because they're all going to intersect at the same point. So that would be point Z. This one says name the orthocenter, so that's where this is where the altitudes intersect. Now it looks like there's only one spot in the middle of the triangle that would be intersecting, but there's only one that would be labeled as an altitude. That's an altitude because we have a perpendicular line from that side to the vertex. We need at least one more altitude, and it happens to be a right triangle. So this is the perpendicular line, the height of that triangle. This is another altitude. So that means that P is where the altitudes intersect. S would not be. S is where one altitude and one median intersect, but that doesn't really, we don't need to worry about that at all. That doesn't answer our question at all. All right. There is one more question in your, or is this the one that I'm looking at? This is number 10 in your notes, I believe. And it says the vertices of triangle JKL are right there. Find the coordinates of the orthocenter of the triangle. Now I must have missed out on number 9. I'll have to check to see where number 9 went, because those are asking for the coordinates, finding the medians and the altitudes. We'll come back to that one. Let's see how much time we're at. All right, we're gonna at least start this one. So this is kind of like we did finding I think we found the circumcenter in the last section. It is a lot of work, and it's a lot of algebra. And you got to be prepared to do a lot of algebra with the distance formula, with slope. So we did find the circumcenter, I think, last time. This one is the orthocenter. So I'm just going to have you write down the steps. It's not in there, but these steps will help you find the orthocenter. So it says first graph the vertices. Then it says find the equation of the line containing the altitude of JL. Okay, so we have to find an altitude. Then we have to find another altitude. So it's going to be a perpendicular line. And then it says find the orthocenter by solving the system of equations. So we're going to have to know some things about slope and linear equations definitely to solve this, because you're going to have to find two linear equations and you're going to have to solve. I'll start you off and we'll graph the vertices. So we have 1, 3. Looks like my board's a little off. 2, 7. 1, 2, 3, 4, 5, 6. It's right up there. And then 6, 3. 1, 2. That's our triangle. Not perfect. But looking at that, we are going to have to find the equation of the line containing the altitude of JL. So if this is J, K, and L. Now technically you could do it for all three, but you just have to do it for 2. So if we find the altitude of that would be the easiest one if we're going left to right. Right here. Vertical line going through the vertex, and it's perpendicular to that other side. That's the easy one that we could find the equation for. Now the harder one would be finding the equation for let's just do J or KL. So it has to be perpendicular to KL, and it also has to go through point J. So I'm going to leave that for you to try. If you want to try that on your own, we'll go through parts of it in class next time. So that's all we're going to do for today. We'll see you next time.